Okay, everybody, let's take a look at the microscopic picture to a current. So what's actually happening in a conductor as charges are moving from one place to another? So let's look at this in depth. We're going to take an amount of charge delta Q. This is the total number of charge that is available, the total amount of charge that's available for conduction. So this is in some volume of a conductor, the total number of charge carriers in that volume multiplied by the charge per carrier. So if I have, remember that if I have, that each electron is 1.602 times 10 to the negative 19th coulombs. So if I had two charge carriers in that volume, that would be twice that, 2 times 1.602 or 3.204 times 10 to the negative 19th coulombs. Okay, there are there are in charges, little in charges per unit volume. So the total number of charge carriers must be equal to that little in multiplied by the volume, by how big by how much volume we have. Now, we're going to express a volume element as a cross-sectional area times a length. So we're going to think about this volume of charges that are moving over to the right. So it's got a length. They're all going to move a distance x that's equal to their speed times the time it takes for them to move that distance. And that's going to describe our little volume element here. So just as shown, the distance they travel is equal to this speed that we're going to call VD, which, as you might guess, is the drift velocity. The drift velocity multiplied by the time it takes to move them that distance. And so now we're going to combine these pieces together. So we have the total charge available that's going to be moving through that volume. It's equal to the total number of charge carriers multiplied by the charge on each carrier. We're going to substitute in delta V in for here. We're going to substitute x times a in for delta v. We're going to substitute the drift velocity times delta t in for x. And when I do that, when I put 6, 7, 8, and 9 together, I'm going to get delta q is equal to in delta v times q. This is our volume element. This is a chunk of volume, is equal to in delta x times a, there's our volume, times q, is equal to in times the drift velocity times that time, aq. So I'm just plugging one of these into the other, into that first. And I'm going to solve this for delta q over delta t, because this is the amount of charge moving in some amount of time. This is a current. So I can quickly find that the current is equal to the number of charge carriers per unit volume multiplied by the drift velocity multiplied by the cross-sectional area multiplied by the charge on each carrier. So in general, that Q will be the elementary charge because we have single electrons that are doing the moving. Okay. So we can solve for the actual speed at which the electrons move down the conductor by just solving for that drift velocity. So this VD is describing how fast the charges are moving through the conductor. So let's actually try this out. I've got to take some 12 gauge copper wire with a mass, copper with, we're looking at copper 64, has a mass density of nearly 9,000 kilograms per cubic meter. That 12 gauge wire has a diameter of a little over 2 millimeters. And we're going to let it carry a 2 amp current, which is a moderately substantial current. We want to know how fast are the electrons moving in the wire. Okay, so we can determine the cross-sectional areas should be pretty easy at this point, unless you're like me and you forget to turn a diameter into a radius. How do we figure out how many charge carriers there are? How many charges are there in that copper wire per unit meter cubic meter per unit volume that can run down the length of the wire to carry the charge. And I apologize for the typo there. Okay, this is kind of fun. So the number density of the particles, a number per cubic meter, should be equal to the total mass of copper per unit volume divided by the mass of a single copper atom, right? All the copper if you have a mass of copper in your hand, to find out how many atoms you're holding, you need to take that total mass and divide it by the mass of an individual particle, of an individual copper atom. All right, so because we're working in terms of number density and not just number, we can work in terms of mass density and not just mass. So the number density is equal to the mass per unit volume, which is equal to just the mass density rho. All right, so I've subscripted this rho by an m to indicate that this is mass density and not resistivity. And MP, of course, is the mass of the particle, the mass of the copper atom. Okay, now the mass of a single copper atom is equal to the molar mass divided by Avogadro's number. So our molar mass with a capital M divided by Avogadro's number. The molar mass of copper is given by its atomic mass in units of grams per mole. So here we go, take a look. We've got copper with an atomic mass of 64. That means that its molar mass is 64 grams per mole. 1 mole of copper has a mass of 64 grams. That's 64 times 10 to the negative third kilograms per mole. We want to be in MKS units. We need that kilograms out there. So the mass of a single particle is equal to 64 times 10 to the negative third kilograms per mole. That's our molar mass, divided by Avogadro's number, 602 times 10 to the 23rd per mole. The per moles cancel out, and I'm just left with about 1.063 times 10 to the negative 25th kilograms. That's the mass of negative 25th kilograms. It's a mass of a single copper atom. So now we can go and we can find out what the number density of copper atoms is. That's our mass density divided by the mass of a proton. The mass density of copper is given. That's our 8.96 times 10 to the third kilograms per cubic meter. That's our numerator. And our denominator is the mass of a single copper atom that we just calculated, 1.063 times 10 to the negative 25th kilograms, giving me a total of 8.43 times 10 to the 28th atoms per cubic meter. Now, the reason this is important is because each copper atom is going to donate 1 electron to conduction. So if we want to know how many electrons there are to conduct electricity, we needed to know how many copper atoms there are. So the answer is there are about 8.43 times 10 to the 28th electrons per cubic meter. Now, some metals may donate more than 1 electron to the conduction band, in which case we would double that. That N would be twice as much. But for us, we don't have to do that. Copper basically donates 1. And so we can go right to our drift velocity equation now. We know that the drift velocity looks like the current divided by the number density of conduction electrons multiplied by the cross-sectional area multiplied by the charge per charge carrier. So in a conductor, the charge carrier is an electron. In an ionic solution, the charge carrier will not be an electron. It'll be some ion, and that ion may have a charge greater than the elementary charge. It may have 2 elementary charge. It may have a +2 charge and -3 charge, whatever else. All right, so we can plug these values in. 2 amps over, there's our number density that we just calculated, 10 to the 28th per cubic meter. There's a cross-sectional area, which I calculated separately. And there is a charge per carrier, the 1.602 times 10 to the negative 19th coulombs. When we evaluate that, we come up with a velocity, the speed of the electron, at close to 5 times 10 to the negative 5th microns per second. So about 44, 45 microns per second. And that's really slow. Let's think about that for a moment. That's ridiculously slow. When you flip on a light switch and the current flows from that switch to the light bulb, the light bulb turns on almost automatically. At 44 microns, 45 microns per second, it's going to take a year before the electron actually gets up to the light. So how does it turn on so quickly? The answer is that when you turn on the light switch, the electrons don't have to move all the way up. The electrons are already packed through the conductor, and all you're doing is shoving on one end, and that causes electrons to move through the light at the other end. So it's not a matter of, say, waiting for people to move down a hallway. It's a matter of having a hallway that's already full of people. And so when people at one end start moving, that just pushes everybody else through. But even then, that seems really slow. Let's go and calculate something else really quickly from last term. If the wire is at room temperature, the electrons in those conduction electrons are basically acting like a gas inside that conductor. They should be moving at an RMS velocity that looks like the square root of 3 kT over m. If you go back and look at our kinetic theory of gases from last term, you'll find that expression. You probably remember that expression. So exactly then, how fast are these electrons moving? In a room temperature wire, 300 Kelvin or so, the individual electrons should be moving at a speed of about 116 kilometers per second. That's about 1 times 10 to the 5th meters per second. These things are zooming around. They are going ridiculously fast. They're going way faster than escape velocity, so it's a good thing they're not bound to Earth by gravity. They're bound by these electrostatic attractions. So they're moving at about 1 times 10 to the 5th meters per second. Drift velocity, though, is about 4 times 10 to the negative 5th meters per second. What's going on? How can these particles be moving so fast, but moving so slowly down the wire? What we see is that the particles are moving in random motions. They're exhibiting random motion. The electrons are not moving in a straight line down the wire. They are traveling through the conductor, and they are bouncing off of everything. They are bouncing off of other electrons. They are bouncing off of atoms. They are not moving in a straight line. So each individual motion of the particle is traveling at this really fast speed, 10 to the 5th meters per second. But because there are so many collisions, and these electrons are almost as likely to bounce backward as they are to bounce forward, the overall motion is slowed by 10 orders of magnitude, from 10 to the 5th down to 10 to the negative 5th. So we have this very slow drift velocity. So these particles are basically bouncing around, and the electric field drags them just a little bit, drags them slowly down the length of the conductor as they're bouncing around within that conductor. And that's what drift velocity is all about.